welcome. Can you please keep quiet? It's a big pleasure of mine to welcome here a colleague of mine, Julien Petillon, who is a professor at the university in Rennes in France. And I met with Julien some 15 years ago, I think.
Something like this.
Yeah, it was at the Archaeological Congress, and that of course means that he's working mainly on spiders, or other arachnids. At that time he was a PhD student, I think, or very near to finish his...
Yeah, it was actually 20 years ago, almost. It was
so
in
it
Russia.
Was 20, okay.
Yeah.
Ah, don't tell me that.
Yeah.
Anyway, Julien did his master at the National History Museum in Paris. Then he did his PhD at the university in Rennes, and then followed a postdoc position in Belgium, actually, where he stayed for 2 years, and then he got a position back in university in Rennes. All the time he was working on spiders, and his major focus was the topic that he's going to show us today. That means the salt marshes, the interaction of spiders that are going on the salt marshes. So I'm very much looking forward to your talk because I haven't seen him for the last 10 years or something, until today.
Yeah.
Here you go.
Yeah, thanks a lot. I mean, it's also a great pleasure to be here. That's actually my first time in Czech Republic, so I'm very pleased to meet people that I really enjoy and hopefully work with in the future. So today I'm going to try to introduce some work we're doing on the ecology, the conservation, and also part of functioning of these salt marshes in Europe. So you might be not aware of what is a salt marsh. So in terms of structure, and today I'm going to talk only about what we call the intertidal salt marshes, right? That means these habitats that are subjected to flooding by the seawater. And I'm making this difference because you do have in Czech Republic some salt marshes that are inland, right? So there's no flooding by seawater as far as I know in Czech Republic. You don't have the sea, right? But still, you have these inland salt marshes. And they are obviously very different for many reasons. So today, we're going to just talk a bit about these intertidal salt marshes. So in Europe, they basically experience a flooding that is, let's say, that occur around once a month, which is quite few. It's not like the US where the flooding is every day. So it's only monthly, once or twice a month in Europe, but still that leads a very high soil salinity and also a plant succession from the high marsh to the low marsh. So that would be basically how a salt marsh would look like in Europe. So they are often a dike, a seawall, that is just stopping the influence of the sea. And then you have this succession from the high marsh, often dominated by some grazing species, still halophilic species, but more grassy plants, to these more pioneerly grown with Spartina and Salicornia species. So that would be the mean sea level. That means like the sea, like on a daily basis, and this is what would happen once or twice a month. So with the springtide, the whole marsh is just covered by water. And of course, you can imagine that the biodiversity there is super specific. So probably, let's say, that's a working hypothesis, adapted to these very constraining factors, both salinity and flooding. And also because these ecosystems are very rare and very linear, because they are just distributed along the coast, that makes that they do have a very high conservation value. And that's also true for in your country for these inland salt marshes. They also have specific biodiversity, and they are also very sparse habitats. In terms of functioning, they are also very special because they have among the highest primary production of the world, because that might reach up to 44 tons of dry weight per hectare and per year. And also, depending on this primary production, there's a lot of secondary production by decomposers, and they are mostly amphipods, so small sea fleas, as we call them. And because of these tidal events, like once or twice a month, a part of this organic matter is going to the marine system around. So there's an export of this organic matter. And this export might be either direct or indirect. If it's direct by the seawater, Odom from the US described this function called outwelling, right? So it's not the upwelling that you're aware of, right? This cycle movement and nutrient, that's an export, so that's the outwelling function. But it might also that the fish are coming to the marsh to feed, so that's called the nursery function because they are mostly juvenile fish coming to the marsh. So what you have to keep in mind is that this big production, and a part of this production goes to the sea, directly in the water, and it goes for enriching the coastal area around, and the other part is taken by the fish that comes to feed upon the prey, and we're going to see that it's mostly amphipods. What about arthropods? That's mostly my focus. We do know from a couple of papers, I didn't put the history of salt-marsh entomology that I'm actually used to include in my presentation, but from some German papers that we were talking during lunch, we know that there are quite few but very abundant species. In other words, strong dominance by just a few species, which was quite classical in very constrained habitats. We make kind of a dichotomy between the US and the European salt marshes in the way that arthropods in the USA are clearly marine species, like these crab eating the Spartana. There's also a lot of gastropods. And in Europe, we guess they are mostly land species. But what we can say is that broadly they're not well known and very few studied, except some papers in the 70s and in the 80s about the ecophysio of these species. So this is where we're working, right? You know, France, England, Belgium, and Netherlands. And that's basically the sites we were working for the last almost 20 years now, mostly focusing on 15 of these sites. But today, I'm going to focus a bit more on this site, which actually is close to our university. It's only 1 hour driving of Rennes. It's called the Mont Saint-Michel's Bay. It's a very famous bay for different reasons, and also for us because it has been long-term monitored thanks to this guy, Professor Lefebvre, who started to study salt-marshes in the 80s, and we're very happy to kind of trying to do the same. It's a strong legacy that we have from this man. So this is how it looks like. So here you have a very famous castle called the Mont Saint-Michel, which is actually in the border between Brittany, so our first region, and this is Normandy. So that's basically the enemy, right? The other people are living here. They are from the Middle Ages and so on. So let's talk about Brittany here. So more civilized people, and which is very special there. It's called a microtidal regime. So we said that the sea was coming and then going back, right? And there's a kind of amplitude between the low and the high sea. And in this site, the difference is 16 meters, right? So you imagine that when it's low tide, the lowest tide ever, and the highest tide ever, it's 16 meters of water difference, right? So that's just the second greatest value in the world. There's another big microtidal regime in Japan, and also in UK, but that's just huge. And that, of course, makes a very big intertidal area. And this intertidal area, there are 2 parts. The mud flats, there is no vegetation, right? It's just muddy. So that's basically here. I didn't show it, sometimes I show it. And what we are interested in, salt marshes, so with vegetation in green here. So more than 4,000 hectares of salt marshes, so that's just huge. And that's good because we can work on the distribution of these arthropods for some land sea transect of more than 1 or even 2 kilometers each. So we had up to 16 sampling stations there. And why is that cool? It's cool because we have huge gradient of salinity. So we can really encompass a very big variation in this stressful factor. And one of the first results we had, it's pretty obvious, is that as the salinity is increasing, then the species richness is just decreasing, right? That's obvious for spiders, that's in blue, and that's obvious for ground beetles, carrots, that's in green. But also, if you look at the species composition, and especially these specialized species, the halophilic species, you can see that they are just increasing in terms of percentage for both groups. And also, this is the spiders, and this is the carabids. You see that for carabids, almost 100 of the individuals belong to a halophilic species. So that shows that, especially for the carabids, the stress is so high that only specialized species, meaning that you don't find in other habitats, are able to survive and to be there. So, of course, we're going to see after why is it so stressful and why are they present. So, I'm used to indicate the reference just because in such a talk, a seminar, we're just constrained by time. So if you want to see more, we can talk, but you can also see the references below. So more and more halophilic species as you go down in the marsh, and the salinity is rising, and especially true for carrot beetles in the way that they are only specialized halophilic species when you're super low in the marsh. Okay, so if we see how these arthropods are reacting to soil salinity, we can basically make 3 groups: the halophilic species, the halotherm species, and of course the halointerem species. So we were interested for the 2 groups if there were kind of adaptation or if it's just plasticity that allowed these species to go there. For this, we focus on one family, which is the family of morph spiders. They are called Lycosidae. And for different reasons, we choose them as a model group. The first thing is that they are basically, especially in Europe, living on the ground, right? So they're really directly exposed to salinity. They're not living on the vegetation, again, especially in Europe. And they are very abundant, and a lot of species there. They do have halophilic species, which was one of the main conditions to study them. Interestingly, they carry their cocoons. So here there's the egg sac carried out by a few males. So that means we can work on their fecundity easily. And the last but not the least, they have different ways to disperse. They can use the air, that's called ballooning. So they're just basically flying by the air, by the winds. They can use the ground, they can run, they can walk. And also, we guess that they can make rafting, so that means dispersed by seawater. So let's first check in the lab how they resist to salinity, right? Here, that's the little time, 50, so that's the time needed to kill half of the spiders that you put for the different treatments, right? And here is the salinity gradient we made in the lab. So null salinity, medium, and super high salinity. And we tested this resistance to salinity for different species. And what you have to know is that Rugubris is a forest species. And Rubeckensis is basically an halotherm species. And Fulvoniata, the red one, is a halophilic species. So what you see is that for basically the 3 species, and that was not really expected, the highest salinity you have and the lower is their resistance and their survival. And that's true for the 3 species. unless you can see this small pattern for Purbecensis, the yellow species, with no significant difference between the medium and the high salinity, but still decreasing between the null and the salinity. That's the first interesting result. But the other one is that, especially in the hypersaline condition, you see that the survival of the halophilic species is higher than the forest species, which is actually super low. In other words, they almost no survive more than a few days in the hypersaline condition. So that means that the survival is decreasing, but still better for salt-marsh species. That's an experiment we did several times with different species, and we always find the same pattern. That's just another experiment, and that's interesting because they are sister species. They are super, super close. They are very similar from many points of view, and the first one is morphology. So one is only occurring in salt marshes, but those are Purbecensis, and the other is quite a widespread species, and you have it also in Czech Republic, but those are aggressive, especially in the fields, right? And again, we do have the same pattern. If you just look at Purbecensis, you see that the survival is basically decreasing with the increase of salinity, and the same goes for the other species. But if you compare the survival at null salinity, the aggressive is better, and the opposite pattern is found for the highest salinity, with higher survival of the salt-marsh species. So we wrote that the tolerance to salinity partly define the niche of the species in the way that we can explain why the generalist or the forest species are not found in the salt marshes, right? Just because they're not able to survive. But partly in the way that we're not explaining why the salt marsh species are not found in other habitats than the salt marshes, given that their survival would be even better. And we did find the same result for the fitness. We found an important role in terms of osmoregulation of sodium. Okay, that's classical for osmoregulation of these arthropods, but also that other amino acids and sugars were involved in osmoregulation, and they were differing between the species. So that was for the salinity, right? The other experiments we did a couple of times is just seeing how it works when we put them underwater, right? So that's the reason why we called it resistant to submersion. So that was a forced submergence. They couldn't go to the surface to breathe. They were forced because of the mesh, so they were just underwater. And we checked over hours, right? So that's almost 2 days, 2 full days, how different species, again, salt marsh and forest species, were active underwater. And again, the same pattern is that the forest species, and that was of course expected, quickly die underwater. The haloterran species is quite medium, intermediate survival, and then look at the halophilic species, it survived up to 1.5 days underwater, again without breathing, in seawater. Interestingly, we found that one species, only the largest one, Arctosa fulvolinata, was over time falling into a coma, but then it was kind of getting back from the coma and surviving again. So that was a hypoxic coma that was not described on spiders. So that was quite unexpected result. So that was when you forced spiders to go underwater. But what's happening when the sea level is rising? In other words, when they can choose. So what would be the behavior when the sea is coming? So we tried to test this on the field with some experiments of manipulation, but it didn't properly work. But in the lab, we had some results. So first, as classic pre-experiment, we defined the histogram on different species, but I'm going to show you the results for Arctosa fulvolinata. So we found some spiders that were climbing along sticks during immersion. That's what we call the climbers. We found some that were just avoiding actively the immersion. That's what we call the floaters. And then few were withstanding the submersion. That's what we call the divers. So that's basically the setup. And I'm going to show you some movies on how it works when you put the water. It's always challenging to put movies in a presentation, but we're going to do that. So this is the floating behavior. So nothing happening except just staying on the water, trying to escape, but still floating. It's not high quality movie, right? But you see the idea. So that's now the diving behavior. So you're going to see that it's really diving, trying, and then finally it goes underwater. Other were just, oops, it goes very fast. You can see that just before that we put the water, it's already prepared to be submerged. And it's just sticking to the leader. And you can see also the air bubble around the body, obviously. And then, that was kind of unexpected. When they are underwater, they're just doing fine, and some are just exploring the habitat. They are, I mean, they look happy, right? So, in a way, that's good, because that's what they experience like every day. Not every day, but regularly. So, what we wanted to see is if the habitat is changing, will this behavior change as well? So, in terms of proportional reactions, we compare these three behaviors displayed whether they were a litter, that's the pale gray, or with a litter, that's the dark one. And obviously, we found a habitat-dependent behavior with much more diverse. When there was a litter, they were more willing to withstand their submersion. No effect on climbers along sticks, but the difference was for floaters in the way that they were much more floaters when there was no litter compared to the presence of a litter. So as I told you, we were also interested in the fitness of these lycosids. And basically what we did is that we compared different levels of suitability in salt marshes for these lycosids. And what we did is that we counted the number of eggs the females were producing, and we also measured the average volume of these eggs. So the first thing we found is that the number of eggs was positively and linearly correlated with the female mass. But that was not the case for the volume of eggs. And the other results we found is that in case of a suitable habitats, so that's the black regression, the number of eggs was higher, but their volume was lower. So there was a trade-off between the number and the volume of eggs, depending on habitat conditions. So that was an indicator of habitat condition for these salt marshes. So we use that for different studies and also different contexts. And we always found this relationship between the female mass or the width of the carapace, prosoma, and the number of eggs. So we did that on different lycosids in other regions and other habitats, and it works well. So, as I told you, we were also interested in the dispersal of lycosids. And the funny thing on this species is that we worked on both the dispersal long distance, the ballooning, for both adults and juveniles. And we found a pretty, let's say, classical relationship between the activity density, the local density, and the chance to disperse. So the more spiders there are around, and the higher the chance to disperse there is. So that's a density dependence classical relationship. But for juveniles, it was actually the opposite pattern. So that means that the more spiders, the more juvenile they had around, and the less they were ballooning. So that was quite interesting. And also we're starting to work on the chemistry of mothers, because it might be that there are some communication between the mother and the juveniles for kind of informing them that the environment is good. So for this first ecology part, I suggest the following take-home messages. Oops. Oh, yeah. So we really want to know more, how to better understand how lycosid went to this specialization in terms of very particular habitats. And also, I would love to talk with Stano about the foods. That's a factor we started to introduce in our experiments, but from the field we actually don't know what they are eating. And at least one, so that's a Padosa eating another lycosid, a Pirata piraticus, that you may know. But we guess that at least one species is eating only, or at least a lot of antipodes. And that probably has strong consequences in terms of functioning. So we would love to go a bit more into this question that we just very few started to investigate. From what we saw here, and that's pretty much, that was not really expected, we found much more plasticity than adaptation to these constraining factors of both salinity and flooding. Also, that our guess, and that's something we found in other habitats, is that the dispersal, the way assemblages are structured or driven, and the way species are competing is very different for spiders than other groups that they are sometimes compared with, especially like carabids. We guess the drivers are super different, and we should really know more and not make shortcuts and parallel. So let's talk a bit about the conservation of these salt marshes. So what happened in many West European sites is that there were an invasion by a grass, might be a hybrid, we don't know exactly, but for sure these natural salt marshes dominated by shrubby plants, mostly a triplex, are now dominated by some grasslands, monospecific grasslands of these Poaceae. So that is really frequent in many sites, and a German PhD student really started to work on these invasions. So there are different reasons for these invasions. The polyploid story is one of them, but let's say the Dutch connection is more into a decrease of human practices. So they argue, we're not especially agree, but yeah, that's their opinion. They argue that the lack of mowing and grazing is just maturating more, aging more salt marshes. And another theory, or at least explanation, which is actually not, they are not excluding each other, is that this grass is obviously nitrophilous, so it might use the nitrogen of the soil to better osmoregulate. So it might be that an increase in soil nitrogen, whether from the rain, from the sea, from the river, from the catchment, might also benefit these plants. Anyways, what's sure is that it strongly modified the habitat. First, the above ground vegetation, that's pretty obvious, right? But also at the ground level, because it creates a litter up to 10 centimeters that was not present before, and also it changes below ground structure by the sediment composition and the root system, which is very different from the natural habitat. So our question was, what's happening when you go from there to there from the arthropod point of view? And we were kind of lucky because we could use two approaches. We could compare the two habitats at the same time. That's a synchronic approach. But we could also compare one single habitat, one single site over time, and compare these that became that over time. So we mostly work on this bay I was introduced you, and we could compare 2 years at the beginning of 80s and the beginning of 2002, 2003, that was the end of my PhD. So if we compare the spider assemblages between the two studies, we could work on shared species, right? Because few species was kind of exclusive to each study. So it might be misidentification, it might be accidental species, we don't know. But we kept the main part of the spider, 36, which is quite cool. And some of the species that were restricted to the dike in '84 were still restricted to the dike almost 20 years after. They are mostly land species. 9 species were distributed over the entire marsh in '84, that the blue distribution, and were found along the same transect with my study. And the third case, which is the most intriguing, is the case of 20 species that were just restricted to the dike before the invasion, and that invaded the whole marshes afterwards. So, if we look at the percentage of halophilic species, you remember we said that it was increasing over the marsh from the high to the low marsh. We say, yeah, it's normal, it's just selection of specialized species. But it's interesting to see that if we compare it before the invasion in blue and after the invasion in red, you see that it decreases, especially in the low marsh. In other words, the halophilic character of these salt-marshes just decreased because of the invasion, or at least afterwards. More recently, we worked on the impact on the invasion, but also of other grazing on the local communities. And what we did is that the natural habitat is so fragmented now that we wanted to see if just the landscape composition could affect the local fauna, even if it's still natural vegetation. And the answer is yes. That means that the invasion also impacts locally natural vegetation, even if it's just a landscape effect. That was quite surprising, but we found that for all the taxa that we studied, and that includes amphipods, spiders, and carabids. That's just the results for the abundance or activity density of amphipods and carabids, but we found the same for the spider. That's a paper we just published. So of course, when you see this, we wanted to work on different way of management, so we quite extensively, in different sites of France, Belgium, and UK, worked on the management by sheep or cattle grazing. Cattle is quite unusual in these habitats, but still, that was an option. And also mowing or cutting, depending on how you call it. And also, we worked on restorating salt-marshes, and that's a bit what I want to talk to you about in the UK. But but there are other papers that I don't want to introduce you. So in UK, they started in the 90s to remake some salt marshes. And the idea was not to make nature, right? It's because of sea level rise, they want to buffer the increase of sea level rise. So they were thinking, let's reopen some salt marshes. So what they are basically doing, that was a dike, remember, a seawall. So they're just breaking the dike, make a hole, so that the sea is coming back to the marsh. And they're doing that in different sites of UK just to buffer the rising sea level. So the idea was this. And of course, we wanted to see if it was working for the salt marshes. In other words, if they were recovering natural vegetation and animals and functioning. So that's UK and that's France. France doesn't have bees, so we had to wait for big storms to destroy dikes, but because it was not planned, destroying many settlements and construction and building, and people actually lost not only their housing, but also their life, because that was not expecting, and people were living too close to the coast. That's a picture from Charente-Maritime, so that's a bit south of western France, and that's what happened when a big storm came a few years ago, Cynthia. But UK, you know, they are different, so they're planning things. So that's a study we did in the county of Essex, so that's southeast of England. And we worked along the estuary of Blackwater River, and we studied 10 sites that were bridged, so opened the dikes. And the dike was destroyed, open from 3, so that's managed realignment, to 100 years. And for all the sites, we had a reference, so in other words, a bird match, natural salt marsh that we could compare with. So what we found, if we look at the percentage of the halophilic species, species richness, or percentage of halophilic species pool over the time of restoration, is that actually the arthropods are recognizing super fast, and especially spiders, so probably they are not dispersal limited. That means that they're coming, they are among the first recolonizing the salt marshes. And also what we found, it's not because you have the fauna that is still working or not still working. In other words, there's no equivalency between restoring the structure and restoring the function of these salt marshes. So if we're still on time, and I think we are, we're gonna finish by a few words about how these habitats are functioning. What's happening with all this organic matter that they are producing. That's something we're working a lot in the last years. So let's just recall what we said, very high primary production, also very high production of antipodes, and that's is exported to the sea by seawater, that the outwelling function described by Odu in the East American, Northeast American salt marshes, and by the fish when they were coming to feed with the sea. That's a nursery function described by example Haynes, but other few authors. There's many things we don't know. This outwelling function, I told you, was described in the US, and it's still well studied there. This colleague, Brian Silliman, is working at Duke University, North Carolina, and is working a lot on how the bivalves are growing if there are some salt marshes around. So it's actually not, proper experiment, it's just correlative approach, but he described several times that if there were some salt-marshes around, these bivalves are growing faster because of these trophic enrichment, so this outwelling function. But for Europe, we don't know. We guess that's the old dream of Professor Löffel. I'll show you the picture, that it works the same in Europe, but actually we don't know. Really, it's more believing than really proving things. So we're working with Brian to make more comparison with the US, but still we're lacking evidence. Fish nursery, well, there have been a lot of works in the USA when they were restoring the salt-marshes, so they were monitoring the fish. Pascal, a colleague from Rennes, worked quite a lot on the grazing effects, but still we don't know the impact of other disturbance and activities, so that was basically the research lines we followed. So how does it work? So we have this high primary production that is partly storing in a litter, then you have some decay processes, and then the carbon, either dissolved or particulate, is exported by this outwelling to enrich the marine food webs, right? That's easy. So let's go back to this invasive story and compare the primary production, because one big question is that what's happening with outwelling because of the invasion. So if we look at the production of dry weight per square meter and per year between the invasive species and the control, that's Atripex, we found, and that was quite unexpected, that the primary production is actually higher under the invasive plan compared to the control plot. So, okay, it's actually even increasing. Okay, that's good. And then we wanted to solve, remember, the next step is decaying process. So what's happening as a rule, I mean, usually the matter is decomposed into along three steps. The first one is just leaching of larvae components, and that's the reason for a very fast loss of organic matter. So the percentage of remaining dry matter is quickly decreasing. Then there's the plateau during which bacteria and fungi are developing, and they are just increasing the nitrogen content. And when the ratio carbon to nitrogen is low enough, then the other fauna, like nematodes, are just finishing the decomposition. And using some little bags of both control that they grew and invasive vegetation, that the pink migration, we found a pretty same pattern with these 3, 1, 2, 3 steps. But as you can see, the decomposition of the invasive plant is much slower. Look at here, after the first step, we still have half of the dry matter remaining, while when it's more between 20 and 30% at the end. That means that after 1 year of decomposition, there's almost no, let's say, 7% on average of natural vegetation left, when it's more than 20 for the invasion. So slower, and at the end, more litter remaining, which fits well to what we see on the field, right? Well, that might be explained by different things, and we were interested in the meso and microfauna, so we did core sample around some lengthy transect, and basically we found especially that the arthropods that were very dominant under the natural vegetation were strongly reduced, and they were more gastropods, but they were less active. And the same pattern was found for springtails, Columbola, that were reduced in terms of relative abundance under the invasive vegetation. That was the core sampling. We found pretty much the same results in the sediment, so that basically looking at the production of CO2, so that's an indicator of how active are the bacteria, and that was true for the different depth, with these invasion, control, but so it's obviously always smaller, but look at the scale here, it's much less. Here it's kind of medium, but the main difference is here with 4 times less CO2 respiration in the first centimeter of soil. So what we have as a broad picture is probably, we told you that it was a nitrophilous grass, more nitrogen input from catchment or for elsewhere. That's probably somewhere leads the invasion by an enemy, but it's changing many things. But still, the production is higher, but the quality of the vegetation is lower with poor carbon compounds. We didn't talk about it, but there's also some phytolites. Do you know phytolites? Some small stones that are in the grass, sorry. So that is also reducing the quality and making harder to decompose, and overall decreasing decomposition process. So finally, the salt-marsh is sequestrating more carbon and making it maturing faster. So basically, because of this invasion, probably due to eutrophication, we're going from a source to a sink of carbon. And the question is, and that's going to be our last part, what's the impact for marine food webs, and especially for these fish? So the reason why we're working on fish, it's because it's quite funny, of course, to see that a part of the land matter is going to the sea by these fish. But it's also important for people around, because some of these species, like the sea bass, are very important for the local economy, especially in Brittany. So we also know that the salt-marshes are really changing. This is an example of this invasive grass, but also with other disturbances like this overgrazing. So that's basically turf. You could play golf easily because the grass is so short. So that also has an impact on these fish. So first we wanted to see what they are just feeding. So we started doing gut content. So you just catch fish in these creeks, right? You put a net. Of course you have to make a lot of paperwork, a lot of permits. And then you fish in here, you take the fish. That's very nice feed work, right? And you open them and you just see what they have in the gut. What we saw, and that's a PhD student, is that for the sea bass, they're changing their regime with the size, the body size. So basically they are eating a lot of marine prey when they are small, and more land, and especially arthropods prey when they are growing, but still juvenile, right? And that was true for the different use we studied. So let's focus on these small sand flea, these sandhopper called orchestia, so these small arthropods. So yeah, it's indeed the main food source for several fish species. And when we say that it's the main food item, it's because when you're opening the guts, we found a lot of them, right? But you're not opening the gut when they are not there. So that means that the snapshot is just valid for the moment when you see them, right? So what we did basically is we wanted to see how accessible they were and how much they were present between the same invaded and natural habitats. So what we did for estimating how mobile were the specimens, we put some pitfall traps that we often use for spiders, right? So pitfall traps are good in the way, especially for these, in the way that they are just capturing the amphipods that are moving. And our hypothesis is that only the amphipods that were active were likely to be eaten by fish. Right? So that was good to have this activity density in both natural and invaded vegetation. This is how it looks like. And also, we did an experiment to see if there was a relationship between the number of amphipods that were falling into this trap compared to the biomass around. And yes, we found a relationship. In other words, we can use this pitfall trap for estimating biomass, but just for this amphipod. We tried for spiders and it didn't work. And what we found, again, is that under the invaded vegetation, there was a strong decrease in the amphipods, but still, there were quite some. So our guess is that although they are reduced, there's some, they kind of enough to feed the fish. At the same time, we found that the percentage of fishes leaving the salt marsh with empty guts, that the vacuity index, was increasing for the two main species we were working on. That the Masarykova, so rising from 13 to 24%, that's not spectacular, but it was higher for the sea bass. See that before the invasion, almost no sea bass was leaving the marsh with empty gut, and it was more than 1/4 of the fish after. We also see that they were changing their main food items. So before the invasion, it was mostly the sandhopper, and after it was a marine worm called Nereis or Hediste diversicolor for the Masarykova, and for the sea bass, they were eating a kind of shrimp, Mysidacea, called Neomysis integer. The last thing we did is that just for two sites, but we are doing that on other sites, is that we are comparing the sites in terms of trophic network. So basically what we're studying is the impact of different invasive plants, so Elymus that you know, and also Phragmites australis, and the impact of sheep grazing. So our expectation was a strong impact on of this invasion and also grazing, but quite few side effects. That's briefly the results of the stable isotopes. So that's basically the carbon, delta nitrogen. So as soon as you are on the left, that's you are more in a landy area. The more you are on the right, it's more C. That's for the carbon axis. And for nitrogen, the more you go high, and the more you are high in the trophic network. In other words, the sink of matter are low and the predators are high, right? So what you can see here, but that's very briefly, is that there is no effect, and we found that 2 times, of the invasion on the structure of the network for both sides. The same went for grazing, where we found no significant effect on grazing. That's the mixing model, not mixed model, right? Mixing model, that's for mixing sources. But we did find a very strong side effect. So when comparing the same vegetation between the two sides, the Seine and the Mont Saint-Michel, we found a very different structure of our network. And you can see here that the marine network is interplaying with the land network, and that was not the case at all in the Mont Saint-Michel. So surprisingly, the structure of the food web were not disturbed by the invasions nor by the grazing. It was the case when they were mixing because of some transfer of food. And here we're back again to this antipode. So in the same way, these amphipods act like a vector between the trophic network. So site was actually the main single variation with mixing for the Seine Bay and not for the Mont Saint-Michel Bay. What we're seeing is that actually, and that is putting us back to this US versus European comparison, is that the frequency of tides is probably key here, because in Seine Bay almost all tides are going to the marshes, and it's less than half for the Mont Saint-Michel Bay. So what we're seeing is that isotopes were super interesting for understanding how complex networking with different sources of organic matter could play. And also, the good thing is that they are giving a signature of a time where they get content in just a snapshot, right? It's just a moment what they just have eaten. Isotopes, it's much more integrative. So, take home messages for this part. We had some very balanced impacts of human disturbances of salt-marsh function, with obvious impacts for invasions, especially on the outwelling function, but less clear for the nursery function. Again, we want to see really these tidal rhythm impact by comparing to other sites that we recently visited for such comparison. So it might be US, but China is also very interesting in terms of frequency of tides. And the last thing we're doing now is comparing the results from the sample isotopes to the fatty acids. And I guess we're going to have also some new surprises. So just to let you know that currently we have two big projects, national ones, so mostly for testing for gene fluxes among sites, and also organic matter between the land and the sea. So we're doing a lot, in other words, of DNA and stable isotopes, basically across the France. But also we're working, as I said, with other partners. So I'm coordinating two European projects. One is named RISE, so that's for exchanging people worldwide. So we do have partners working on salt-marshes in China, US, Australia, Argentina, Chile, and South Africa, and Europe, of course. So UK, Italy, Spain, so that's pretty exciting. And the last thing is that we're also working on a Euroseed grant on the lycosids worldwide. Thank you for your attention. I'm going to watch the time, and that was just a bit more than 1 hour.
You're perfect on time, and thank you very much for this nice talk about this very strange habitat to us.
Yeah.
And we have plenty of time for questions.
Due to their specialization, are there any endemic arthropod species for these locations?
Salt-marshes.
So, you mean endemics for the geography?
Let's say for France. Only for France, salt-marshes.
No. They are basically species extending from, France to the north. So there are two main biogeographic patterns for these species. Either they are restricted to the northern part of France, and then they go to Norway, Iceland, Greenland, and there they are quite widespread and ubiquitous species, and then they are restricted to the salt marshes. The case, for example, of Erigone artica. Yeah, you see the name. So you can find it in different habitats in Iceland, in Greenland, and then in Brittany, it's only in salt marshes, and you don't find it south of Brittany. It's really the border. And the other pattern is more funny. Is species from the Mediterranean coast, that are going up to, let's say, Belgium or Netherlands, and also, but then they are restricted to salt-marshes. But I'm not aware of any endemic in the way of geographic endemicity, right? Not of, but of course they are almost all specialized in terms of habitats.
I was thinking that the fact that the system turns into a carbon sink could be, of course, in the current context, interpreted in a very positive way.
Yeah.
Because it would kind of mitigate global warming effects.
Exactly.
And when it comes to less organic matter, less nutrients, so it would be mainly nitrogen would be the important part here, flow into the water. Well, at least in Europe, taking all the deposition, atmospheric deposition we have, there shouldn't be so much net change in the input of nitrogen, or is there?
Yeah, that's something we don't know. For rivers, it's quite obvious that it really increased for the last, let's say, 30 years. So we do have evidence, but we're really lacking some measurements in the salt-marsh soil. That's a pity, that's a black box. Quite easy still, but yeah, we don't know. But concerning your first remark, actually, I never thought about it except today when I was giving that. I was thinking, yeah, actually it's pretty good, but that was the first time I was thinking like this. But we're working a lot with these ecosystem services and carbon storage. That's the reason why we're really into it. So people from Australia, this guy, maybe you know him, that's Peter McReady, and he's working a lot on carbon sequestration. That's, that's in this project. I'm asking money for this.
Yeah. So not yet?
Not yet, not yet, no. I'm going for a short sabbatical next spring in Harvard, you know, Gonzalo's last. And one of the ideas for the few months I'm going to spend there is doing comparative genomics and just seeing the signal of glycosides under saline stress or not, just seeing if there's a different expression. But we're doing, first and then go deeper. And also what we're doing now is working on this kind of halophilic signal and see in the phylogeny of arachnids and even arthropods. It's a big broader review where if it's randomly distributed or is it specific to some lineage. It's a correlative approach, but still it's a first step. You're right. That's a good question. Another question? Yes?
You were talking about the relationship between salt marshes with fish or spiders or human activity. What about birds? If any birds are important, for example, goose.
Yeah.
There is any story about
Yeah, I did not. I mean, I'm not racist against birds. No, that's just. So one of the guy of the lab, that was almost 15 years ago. He worked on the goose, indeed. But that's right. It's certainly important. So in this right project, we have a part on the birds. But in the network that we built, we don't have many people working on birds. Although it's probably key for managers, for hunters, for many things. But we're missing an expertise in the goose is kind of special because they are really doing well in grazed parts, right? These very open areas, they like it because they can feed upon Coccinellia. They have a good view of, if it's getting too close like these invaded salt-marshes, it's really not good for the goose. Then there are some passerine birds that are doing okay, but that's something we don't. And also for us, Yeah, they're less specialized species, so it's more that refuge habitat, right? Yeah. Still, yeah, many things to do.
Yes, Igor?
You mentioned three different strategies for the lycosis spiders, the climbers, divers, and floaters.
Right.
Is the difference between them only in the behavior or also in morphology? I mean, pubescence,
Yeah,
or
that's a good question. We didn't go to these, and all the other question would be local adaptation. In other words, depending on the place where they're coming from in the marsh, would they behave differently? That would be an expectation, right? And we didn't do that neither. So we just know that there's a good individual repeatability. That's something we check, but we didn't relate to morphology or even to kind of genetic basis, which would be interesting indeed. Yeah, it's a good point. But we were thinking too, but we never did. So.
Another question? Yes.
I was very intrigued by the fact that you're taking the amphipods in the salt marshes as being part of the terrestrial system. Why I was intrigued is that when I was preparing my soil zoology lecture, one always looks for these oddities, you know. And usually when it comes to amphipods, only one genus in Australia, which is in the rainforest, is mentioned as being terrestrial.
I know.
And all the others are considered to be marine or freshwater.
Yeah.
So how terrestrial are they actually? I assume they need water for reproduction?
Yeah, that's interesting. So since I guess I see maybe not the paper because there were a couple of papers, but at least the author in Australia is sticking to Jim Lowry. But since there were other classification of amphipods, and the genus Orchestia is now placed as semi-terrestrial, okay, we don't know, let's say in between, but yeah, if you see it, so it basically lives in land condition, right? And on the other way around, when they are flooded, they are really doing bad. They are bad swimmers. It's like, what's happening there? So they are really land hoppers, actually.
So, well, you know, do they sort of reproduce on land? So similar to isopods, they don't need any free water.
The marsupium.
Just the marsupium with a bit of water there.
Yeah. So sorry to this kind of Swiss reply, but it's no marine, no land. It would be semi-terrestrial.
Well, that's what we get in wetlands, right? I mean, so that's quite natural.
But that's kind of particular for this genus Orchestia. And I know that, but there were quite recent papers on these guilds of amphipods, which is interesting.
Okay, I will have to incorporate that in my lecture then.
Yeah. I can send you the papers. Yeah, good ones.
So you mentioned you study here the lycosites from these salt marshes, that's your specialty and everything. And as far as I know, the lycosites are usually, probably from maybe some small size to medium size. They can go to larger. These one are like medium size usually, something like that, right?
Yeah.
I was curious more because of these changes and everything, and you told me that there are still not really many observations, but maybe from your fieldwork, have you seen on what they are actually feeding there because of their size and everything? Like you studied caribids and spiders. Why would they even inhabit this field which is really regular, like changing in tides and everything? Water levels, what are they feeding there?
So first, in terms of size, that's a large species, right? The Arthropods volinata, it's more than 2 centimeters, so it's obviously a large species. Okay. And that's the species, I guess, is feeding on amphipods. That's my guess. So we did some experiment in the lab where they were fed with amphipods, so they were eating a lot of them, and we also published on the impact on this consumption on their osmoregulation, because obviously it has a strong impact. But we don't know against how it works on the field, and we didn't make any choice experiments, which would make a difference to me. So they were fed either with no amphipods, amphipods from freshwater, Orchesia but from freshwater, and Orchesia from salt marshes. And then the other one, so the Padosa, Purbecensis, just it's better to have a picture, right? But it's coming soon. Yeah. So that's a Padosa, but let's say in the genus quite large because it's a bit more than 1 centimeter. So it's not a small Padosa. It's among the largest species of Padosa. So we wanted to say to perform the same experiment with these species and amphipods. We said, yeah, we have a design that works well. So let's take the other one. So we hire a master student on this topic. And then she gave some amphipods. Nothing. Like, no, thank you. I said, yeah, don't worry. Just put more amphipods and wait. So she put, I don't know how many amphipods and wait for weeks. And no, sorry, then any was eaten. So obviously no amphipods. So that's a picture I took in the UK where it was feeding upon a pirata. But yeah, probably on small, not small, on springtails, on small flies, probably eating whatever it finds, right? Yeah, but that's true that we don't have any data.
Another question? Yes, please.
I'd like to ask about the diving spiders. How long can they stay underwater?
Underwater or on water? Underwater. So what's happening, I went a bit fast on this. So actually there's a big air bubble that is really decreasing over size. So it's just breathing using the air around, and when there's no air anymore, it's just falling into the coma and then recover. So it's basically just breathing what's around her.
How long does it take for the air bubble to go away?
Well, it depends on the species. You see that here it doesn't go more than 10 hours. Yeah, with a little time of let's say 7 hours. Then the other species it's more like 10 hours, and then it goes more. Yeah.
Okay, another question?
May I just ask here this activity rate, because you talked about survival before, but it says activity rate, so I would expect this is just, are they moving around or are they sitting somewhere and...
Yeah,
so is it survival rate?
Yeah, no. Yeah, of course. Though they are not active here, I just wrote activity rate because a part of them is actually into coma, right? Mm-hmm. So that's the reason why for these two species, they are just confounded, and the activity rate would be exactly the same than the survival rate. But for these, then we should correct, and that's the reason why. So actually, just quickly to give you the story of this master student, William. He was really a nice student, very smart, but no lucky at all. So all these experiments went down and were collapsing for any reasons, you know. That happens sometimes. And that was the last experiment ever before he could submit his master thesis. So I came with this very smart hypothesis that the more a spider is exposed to flooding in its natural habitat, and the better its survival underwater should be. That's groundbreaking science, right? No, that's stupid, but that's what we had left. So basically, put different species, and then you know that for correcting, you're correcting by species in the model, but also by the size of each individual, because the larger you are, and the better you resist. So they were coming from the water, so he needed to dry them. And instead of putting them directly in the oven, I suggested I just dry them in my office. And so they were just putting all the spiders around, and after a while, maybe 6 or 8 hours, some spiders were running around like, I said, oh come on, William, you again failed your experiment. How did you do this? Yeah, it's simple to kill some spiders. No, Julien, really? They were dying? Oh, so you mean they were dead? and they're not dead anymore. That's what you're telling me. Yes, but he was right. They were undead, but that was true. So just to say that once we did an experiment where we were randomly picking some samples, right, to correct it either for death or for coma, because we need to check, but we shouldn't wait that one was falling into inactivity to check. So that's the reason why I made a random sampling for 48 hours. And then when we were correcting the survival rate by this coma, then it was making a big difference.
Yes.
So I was surprised that even the species that performs more poorly in the water, they can take several hours without problem. So what do they do during that time? How they behave? They just wait there, or they can even eat under the water? Because I mean, just wait.
You mean when they are in the coma?
No. When they are
underwater.
Yeah, before the coma.
Oh, I didn't ask them.
Because this is something that they spend a lot of time there, and the tides occur very often. So this
No, it's only once or twice a month.
yes, in Europe, but in the US it can be daily.
Yeah.
They have crabs, no spiders.
They do have lycosids in the US salt-marshes as well. Yeah.
So it can represent like an important amount of their time.
Yeah. It's probably, I mean, foraging without, or maybe with reduced risk of predation. That could be a secret life. No, I'm joking, but that's a good question. Are they, because this movie, I mean, it's not a fake movie. They are really active, but I don't know if it's significant if they are doing that all the time and how long they are doing that. I mean,
Just a comment. I mean, it's known for soil animals or epigeic animals that when there is some inundation, some flooding with freshwater. Now I'm talking about freshwater floods. Then, as long as the water is cold, many of them keep active, like oributted mites might be still feeding and so on, as long as the water is cold, because then it contains enough oxygen. Once it gets warms up, then they usually die, because they like the oxygen.
exactly. There've been good reviews on this topic. Yeah, that's right. Yeah.
Another question? Yes.
Just short, maybe correlated to this. What triggers waking up from the coma? You said that your student was drying them, so they needed to be completely dry, or?
No, it was just because, I mean, if he had put them directly in the oven, that would, of course, not happen. It's just a matter of time, so it's not a matter of drying. It's just because otherwise you would not wait 4 hours, so it's just a matter of time. But so it's not that they are smiling afterwards. It's still costful, and it's not. I mean, it's not nothing. So we had data on the survival after recovering from coma, but William, because he's William, his computer was stolen with all the data about till the end. So yeah, we couldn't see, but I mean, there were some damages. Yeah, obviously.
So this is then not something that naturally occurs?
Yeah, that's a good question, because if you look at the lethal time, actually the coma is mostly occurring after a time longer than what they would actually experience in terms of flooding. Although the time of flooding is something, but also there's a time of drainage, and sometimes the marsh can remain flooded or badly drained for days. So it's not completely out of the reality this pattern. It would make sense, but it's probably not something that is happening all the time, because again it has a cost, and it's probably not.
Yeah, that's why I'm thinking what would cause them.
Creating the coma.
Yes.
Yeah, that one explanation, because they are racing with a narrow pathway, would be the maltats, accumulated maltats could make this kind of coma. Yeah.
Did you test how long they can survive the coma?
Yeah.
Without putting in the oven?
That's a good question. I don't remember by heart the number, but let's say that around 1 day it's probably, 24 hours, that's probably the maximum. But in the paper we have this shape of the coma occurring over time, which is different than this curve, you're right.
Just thinking if the coma is an adaptive strategy, which may help them survive from the water.
My guess would be not, because again, it's not deleterious thing that happens. So I don't think it's adaptive.
Another question? And I also noticed. Can I continue? Okay, I can wait. No problem. Maybe I missed it, but which strategy has better surviving rate? Floaters or divers?
We didn't see the interaction between behavior and resistance. We didn't follow and I think then you have to think more in terms of adaptation, because if you are floating, then the risk that you're just taking the currents and the waves and you don't know when you're gonna land. So my bet is, if there's a leader, then diving and staying near the leader, if it's not too long, is probably the best strategy. In terms of, but then otherwise it's dispersal. But that's something we want to see with the population genetic at large scale, if it's really likely that the currents are structuring the population dispersal and exchanges. Yes, now we go.
Okay, also noticed the increase of Fiti. I guess it's a snail, type of snail, isn't it?
Yeah.
Because I know it under the name of Outwelling.
Or Laconia too.
Yeah, so increase with increasing invasive species.
Exactly.
Biomass.
Yeah.
Could you elaborate on this a little bit? Why was it significant?
Yeah, it is significant. It is. I would say under the invaded vegetation, there's kind of algae, green algae, that is not under the natural vegetation, and it might be that these arthropods are eating the algae, because they are algae grazers, I think.
On the stems of the grass?
No, on the leader. On the leader.
Yeah.
Some kind of very small green algae.
So it means more food for them.
More food for them as grazers,
Yeah.
right?
Sure.
Yeah, that would make sense. It's Ovateli? Ovateli,
Yeah. So it's the same kind of strategy as for those amphibians also.
Yeah.
Living exactly in these fluctuating salt levels.
Right. Yeah. We have more and more evidence that amphipods are eating as much litter than diatoms, so they're kind of mixing the diets.
Any other question?
What do you think? What's the differences between coma and anabiosis? Actually, I am asking you in context the physiological process happening into the organism. So maybe the grazing of metabolism or something like that.
Well, in the way that when you stop the disturbance here, being underwater, it takes really a long time to recover, right? If it's just reduced or activity or just anabiosis, if they remove them from water in just a few minutes, they're going to be active again. And there's no reaction at all. So that's a test that we were using with persons just to see if they were reactive. There's no reaction at all. And again, there's this cost that we lost the data, but they were not, super. Oh, actually, that's fake pictures, because that species has never been into coma. We had no spiders coming, but I'm not sure they will look so, healthy. But that's the pictures we used. So we had no pictures of spiders that was recovering from coma. So that's the one we used. So.
What else was fake?
I think that's it.
Any question concerning the topic? Yes, I have one actually. The salinity experiment. I was wondering what's the mode of action of being intoxicated by the salt. So was it via the drinking?
Drinking, exactly, exactly. So right now, I don't remember when we did it. But we set up an experiment where, but so basically what we take some sand, we rinse it, we burn it, and then we add some water with more or less salt. I mean, cooking salt at different concentration, right? So from Perry in the 50s, we know that the lycosids are drinking, they are able to drink water from the substrate. So that's the way we think. But we set up an experiment where the soil salinity was still active, but the spider couldn't drink it just because there were a small space between the mesh and the sand. But I can't remember if this design is just in my head or if we tested it. I see really well the thing, but I don't know if we really made it or not. But that's a good question. So yeah, we should have some answers more precise if we don't have already that. Yeah.
So any other question? Yes?
Is it possible to manage the invasive grass by grazing for restoring the native vegetation?
Yeah, that's a long debate. I mean, once the invasive plant is there, there's almost no way that you can use grazers to reduce, just because they are avoiding them, especially the sheep. They need, it's too grassy, too high, because of these phytolites. It's probably too hard to digest or even to eat. So.
By fire?
By fire, we were talking about this because of Tomáš Master. So Tomáš wanted to put the fire in our marsh. Why not? So that has not been tested. I'm sure that would be interesting but pretty challenging to set up. And the other thing that has been done is cutting and then introduce grazers, and that works more or less well. In another site in Normandy, they remove the soil and the vegetation, but that I don't know what's going on there, and I'm not even sure that they are monitoring what's happening. It was just a manager idea, and because it's quite interesting also to know that this, as soon as the sea can calm in the French area, it's public domain. Right, so whether a beach, whether salt-marshes, whether cliffs, whatever, rocky coast, it's public. So it's kind of tricky zone because you need some permit, but not really. So there's no real control of what's happening, and that's complicated for grazing, for example, because basically people are doing whatever they want, and the sheep they are putting in the marsh, they sell it like salty sheep, and it's super expensive. So they are making a lot of money. Salty sheep. Yeah, it's famous. It's famous. Yeah, salty lamb.
Any other question?
Yeah. I have a very important one. How did you manage to take these pictures of Mont Saint-Michel without tourists on it?
From a distance.
Yeah, that's a very touristic part. But most of these pictures actually were before this big story because they removed the dike that were going to the mall. They rebuilt some parking, so and now it became even more touristy than it was used to be. But so it's sometimes hard to work there because of this, but still it's a nice place. So they removed the road that was on the dike. They made a bridge. Wooden bridge, it's really nice. So for those who's working on spiders, we're making the Congress in 2 years there. So yeah, we're gonna see the.
Yeah, looking forward.
Yeah. Not me, but.
Any other question? If not, then I'd like to thank again for coming.
Thank you.